Okay, in this chapter 34, they're talking about images. And essentially what we're doing is we're going back to the same individual we started off all of our physics discussions about back in the last fall. And that, of course, is Sir Isaac Newton. A lot of the things dealing with images and all of that come from his work with optics. And so, once again, the great man is going to lead us on our on the knowledge that we're going to develop in this area. So, I'll try to get this slide so that it is oriented just a little bit better. But images and plane mirrors. As shown in figure A right here, you've got a flat mirror here, and it can form a virtual image, said to be the object, by redirecting light rays emerging from a source. Image can be seen where the backward extensions of the reflected rays pass through the mirror. And the object's distance p from the mirror is related to the apparent image distance from the mirror. So this distance, here's where the object actually is. This is where the image appears to be. This distance p is going to be the same as this one right here. This angle here is going to be the same as this angle here. For example, and then if something was longer like this, it would be shown in this manner right here. Okay, object's distance from the mirror is related to the apparent image distance by this I equals minus p. The object's distance is a positive quantity. An image distance is a virtual image and is a negative quantity. Only the rays that are fairly close together can enter the eye after the reflection from the mirror. For the eye position shown here, only a small portion of the mirror near the point right here is going to be able to form an image in the pupil of the eye. So, first thing right here, in the figure you are in a system with two vertical parallel mirrors. Okay, the grinning gargoyle is perched at point O right here. Okay, a distance 0.2d from this mirror A. Each mirror produces first at least, so there's going to be an image beyond this one right here, isn't there? Okay. And then there's going to be another, this image is going to be in this mirror, and then you're going to have another one back and forth. Oh. I don't know why this keeps wanting to jump forward, unless one of you guys are controlling that remotely. I hope not. Then each mirror produces a third image. How deep behind mirror A are the first, second, and third images of mirror A? Okay, so the first one is going to be 0.2 behind here, right? The next one is going to be reflecting off of this one and then back again, so that's going to be 1.8. And the one next beyond that is going to, so it's going to be this image, it's going to be this distance, right? Plus the next one, so that it's going to be where that one believes it should be. And then it's going to be 2.2 out there, right? So it's the answer is the first image is 0.2d, the second is 1.8d, and then the third one is going to be 2.2d. Okay? Okay, practical exercise 1, and this is problem number 1 at the end of this chapter. You look through a camera towards an image of a hummingbird in a plane mirror. The camera is 4.30 meters in front of the mirror. The bird is at the camera level, and it's 5 meters to your right, and 3.30 meters from the mirror. What is the distance between the camera and the parent position of the bird's image in the mirror? So essentially what you're going to do is you're going to draw a diagram of this, and it's going to, here's your camera, here's the mirror, and that's that 4.3 meter distance. The bird is closer than that at 3.3, but it's higher up over here. Oops, So the distance is going to be this distance right here to the image, isn't it? Well, that is just a matter of this distance plus this distance, and the square of this distance and square of this distance, right? So it's d1 plus d2 squared plus d3 squared, and all of that the square root. So these are the different distances right here. This is your d2 right here. This right here is your d1 distance up here, and then you've got your this other distance d3, right? D3 right here. Okay. So the next one, isotropic point source of light is positioned at a distance d from the viewing screen A. Then the plane mirror M is placed behind S at a distance d. Okay, so you've got this mirror here. You've got this viewing screen here. How much is IP multiplied by the presence of the mirror? And this right here is problem number 2 in your book. And the intensity from a point source varies as the inverse square of the distance from the source. IP equals A over D squared. Okay? Here, in this situation, you've got 3D involved here, don't you? Okay? Because it's going to go to the mirror, then it's going to come back again. And each one of those is, so it's going to be 1D and then 2Ds back. Whoops, sorry. So that is, so it's going to be the, that's A is the constant proportionality. So this is going to be IBP D squared over 9D squared gives you IP over 9. So the total intensity is IP plus R, or IP plus IP over 9, for a total of 10 IP over 9. So the original, that's the total intensity, and the ratio to the new intensity is just given by 10 divided by 9, which is 1.11. Okay, spherical mirrors. A spherical mirror is a shape of a small section of a spherical surface and can be concave. That would be this one right here. This is concave. Think of this as it is caved in, and this is flexed out. So this is convex. Okay? You have to... this is getting to me a bit. Okay, so we make a concave mirror by curving the mirror's surface so it's concaved. We make a convex mirror by curving a plane so its surface is convex, flexed out. Curving the surface in this way moves the center of curvature C behind the mirror and increases the field of view. It also, 3, moves the image of the object closer to the mirror, and the objects are in the exact opposite then for a concave mirror. Okay, so this one right here, you're this size, and over here, it becomes larger. Here with this one, this becomes smaller. Distances here are P, and this is between that and the image, right? Here is your plane, and this is how far this is away. All of this is based upon the central axis. Okay, so that's this one right here is a magnification of what is on this side. This right here is a reduction of what's on this side right here. So to find the focus, you send rays parallel to the central axis. This is the central axis, and these come in here. And what happens is when this ray hits here, it will reflect off, and it will hit a point here. Likewise, if you have a ray coming in here and reflecting off, it's also going to come through that same point. This is called the focal point. Now, when you have something that is convex, what happens is it no longer is going to be out here. It's going to be reflected out this way. But you have a virtual focus behind where this particular ray occurs. Okay? So, if the parallel rays are sent into a spherical concave mirror, reflected rays pass through a common point, the real focus. If they are sent towards a spherical convex mirror, the reflected rays pass through a common virtual focus point at a distance f, a negative quantity from the mirror. Okay? So for both mirrors of this type, the focal length is related to the radius of the curvature. F equals 1/2 r. It's an important relationship for you to remember. Okay? And it's positive for a concave mirror, and it's negative for a convex mirror, reflecting that it's over here versus on this side. So for spherical, an object then, inside the focal point of a mirror and its virtual image are reflected right here. Here's your focal point and here's this one. The object at focal point F, and the object is outside the focal point. Okay? And then you have one that's actually at the object of the focal point. So a concave mirror can form a real image if the object is outside this focal point. So at the focal point or out here, you get an image. If it's inside the focal point, inside you get a virtual image. Outside you get a real image. Okay? So a concave mirror can form a real image if the object is outside the focal point, or a virtual image if the object is inside the focal point. Concave mirror can only form a virtual image. Everything with a concave mirror is a virtual image. The mirror equation, that's right here, relates an object's distance p, the mirror's focal length f, and the radius of curvature r. And here's the image distance, right? Okay. So this right here relates the object's distance, the focal length, and the image distance. Magnitude of the lateral magnification m is the ratio of the image height to the object height. Magnification is h over h prime over h, right? M is also equal to minus I over p. Okay? So the radius of curvature, by the way, is involved in forming this focal length here. So, spherical mirrors. We've got four different cases here. In this first case right here, a ray is initially parallel to the central axis and reflected through the focal point right here. A ray in case number 2 right here, we're looking at a ray that reflects from the mirror after passing through the focal point and emerges parallel to the central axis. Okay? That's also in that's this one right here, through the focal point, and then it comes back out through here. So you see that something that is parallel to the axis of curvature is going to come back through the focal point. If it goes through the focal point, it's going to come back out through this point. So the image of the point at an intersection of the two special rays you choose. An image of the object can then be found by locating the images of 2 or more of its off-axis points, and then sketching the rest of the image. You need to modify the descriptions to apply them to a convex mirror. Okay? So here you have for the convex mirror, and here you have for the concave mirror. Okay? And then a ray that reflects from the mirror after passing through the center of curvature. Remember, center of curvature is twice the distance of the focal length. So if you know the focal length, you know the